Right, take it away.
Great. Cool. So, morning, everyone. For those who don't know me, I'm Will. I'm a PhD student in the CBL with Rich. And today I'm going to be talking about a couple of papers, namely these two here, that look at combining the kind of well-known in machine learning community pseudo-point approximations for GPs with the slightly less well-known but fairly well-known now, I guess you could call them state space approximations. In some situations, you can really just think of them as like exploiting structure that was already in your GP. And this is going to be for long time series problems. Yeah, so please just like butt in at any point if anything's not clear. And I apologize for like scrolling through slides like this. Unfortunately, I don't own the version of this app that would let me like cycle through slides properly. So what are these papers about? As I said, it's about combining pseudo-point approximations and Markov property in time to get efficient learning and approximate inference for Gaussian processes for time series. So the kind of one slide summary of all of this, and like if you were to take away anything from this, it would be kind of this picture, is that, let's say we've got a GPF, and for the sake of argument, we'll say it's a Matern 3/2 kernel, which is kind of a fairly standard Matern kernel. And it just so happens that for this kernel, if you, let's say we define S at a point X to be fx and the derivative of fx, if you consider this, this we'll call this the state, and you have a bunch of these points. So say you had, and you would consider the probability of a bunch of such points, n of them. This has a Markov property. So something like this, the usual thing. And so the kind of, this is the standard state space trick, and the point here is like, for this Matern GP, it just happened to be the case that if you condition on both the process and its derivative at any given point in time, you'll get a Markov property. Andrew, you've got your hand up.
Yeah, just to confirm, does this Markov property work only if you look at them in order in time, or does it?
It does, yes. So I should be more precise here. Yeah. So these x's are on the real line, and the x associated with each of these is in ascending order. Does that clarify?
Oh, thanks.
Cool. Great. So we've got this property, and then the idea is we're gonna pick a bunch of pseudo points, these u's, and position them in between some of these x's. So we'll have, so this is all the x's here, and we can see that the u's are in between them. And the point is going to be, okay, well, the u's are just points in this, these process and derivative of process things, and we'll have capital M of them. And so this will also have a Markov property. And the other key bit of structure here is what's depicted here. So any of our states, so for example, the third one here, conditionally independent of all of the u's other than its immediate neighbors. So that's just to say that S3 given U1 and U2. Sorry, all of the M's, all of the U's is really just this. So that's really like all of the structure that these papers are exploiting. And this is the basic setup. And if you kind of get this, then everything else is just kind of figuring out how to exploit this structure, how to work with it efficiently, that kind of stuff. So yeah, so as I see it, the main contributions of this work is like the first paper is, yeah, it kind of frames the setup, shows how to do variational inference in this, at least one way of doing variational inference, and shows what the right family of Gaussian approximations are to consider, what a good family of Gaussian approximations are to consider, and shows how to do some kind of natural gradient stuff to find the parameters of that Gaussian. The second paper pushes this a bit further. The thing I'm going to focus on here that it does is it shows how to parameterize the approximate posterior in a particular way that works quite nicely and is an improvement over the first paper. We'll get onto that in more detail. So I'm interested in this line of work just because I do lots of stuff with GPs, and this is interesting to me. Like I really like the setup above. It's just really clean and quite elegant, and the upshot is that there's lots of structure to exploit, and you actually can do stuff with it. Yeah, so I'm just gonna kind of focus on the main ideas without worrying too much about the nitty-gritty. And it's worth saying that the second paper has some stuff that's not variational Bayes specific, which is interesting. That's like power EP stuff and some more traditional signal processing stuff. But for the sake of this, I'm just going to focus on the variational Bayes. Right. So having done the 2-minute introduction at the top, I'll go into a little bit more depth now. So I'm assuming everyone's familiar with pseudo-point approximations. So we'll be sticking with the standard Titsias 2009 formulation, which says if you've got a GPF, we're going to approximate the posterior over it with a bunch of pseudo-points. There'll be M of them, and give them some arbitrary density, Gaussian density Q, and then the conditional distribution over the rest of the GP, given those points, will just be the prior. And so the kind of the standard mental picture here is lots of points, and your GP maybe is quite simple. And really, you think that if you had a couple of well-located, slightly uncertain observations, you could accurately summarize the posterior over F, given all of these many observations. So in the picture I've drawn here, obviously M is 2 and N is really big, and so M is much less than N. And it turns out that all the interesting operations you want to do here are order M squared N if you're using this approximation, as opposed to if you're doing exact inference, where all the operations would have N cubed complexity. So this is a really big win when you can use a small m and get a good approximation, which tends to happen in exactly the kind of situation I drew here. But where this breaks down is if you've got a time series problem, and in order, you can kind of imagine, if you imagine this graph extending off over here, and maybe it's a bit more wiggly than that or something, that when you're carrying off the edge of the slide, as you get more and more observations, you're going to have to lay down more and more pseudo points, so on and so forth. And so the idea here really is that as n increases, m also increases. So we're in this annoying situation where m is proportional to n. And so really this order m squared n stuff is just n cubed asymptotically. Now it might be that you get a like a constant factor saving here, because maybe you do have like far too many observations per like unit time. But for long time series, this basically doesn't work very well. A separate class of approximations, or just some GPs just have this property, such as the half integer return GPs. You can take your time series GP and approximate it as a state space model. Approximate it as an SDE, specifically a linear SDE, and the finite dimensional marginals are just a Gauss Markov model, and then when you have observations, they become a linear Gaussian state space model. And so inference can be done with Kalman filtering in linear time. So this is all order n. So this is the kind of the Markov stuff we were discussing before. And this is really good for long time series. So I'm just going to make a function that wiggles a bit and then have a sensible number of observations. And this is order n, and everyone's happy. We can do inference and work with long-time series. Where this breaks down a little bit, it's still kind of okay, but not really ideal, is if you had like you had far too many observations per unit time, so on and so forth. Then again, like you'd kind of like to have a pseudo-point approximation where you have sensibly spaced pseudo-points to somehow summarize this, the posterior over your GP. And then hopefully, like you've still got order n scaling, but maybe the coefficient of the scaling is lower. So that would be a nice thing to have, which the Markovian GPs or the state space approximations don't really have by default.
Will, can I just jump in with a question?
Sure.
So if you have one of these long time series and you have like a stationary kernel, like return or something like that, you'd have this property where if 2 points are very distant, then the covariance is essentially going to be 0. So you could probably approximate this kernel by like a fairly sparse matrix.
Mm-hmm. Right.
Would that not induce like a lot of savings?
Yeah, it would. So it would.
It would almost be block diagonal, approximately. It might almost approximately be block diagonal because you really have each point is only really going to be like covariance with its nearby neighbors. Yeah,
you could definitely construct some kind of band diagonal. I think band diagonal is probably a better choice, but same idea. Like you could roughly approximate your kernel matrix or something that's band diagonal.
Yeah, sorry, I think I meant band diagonal. Anyways, go on.
That's fine. The kind of the issue there is like how wide you pick the band. Like if you're optimizing hyperparameters, you have to kind of pick the bandwidth to be a function of like length scales and stuff like that. It's something that I think people have thought about, and there's probably stuff out there that does it. It's not quite clear how to make it work really well all the time, so to speak. Like maybe I'm missing a bit of the literature here, but the nice thing about like the Markov structure in these GPs is that it's exact in some sense. Like particularly for the Matern GPs, like this is the structure, and it just gives you linear time scaling.
Okay, that makes sense. Thanks. Cool. I think Wessel also wants to speak.
Yes, Wessel, go for it.
Hey, quick question. Do you know of any other examples than the Matern kernel family of kernels which are stationary and Markov?
Right. So I, off the top of my head, No, so the ones that there are the main results for are all of the half integer returns. So, sorry, the odd half integer returns. So return half, 3/2, 5/2, etc. You can obviously, so the kind of I'm going to answer your question by like describing the family of kernels for which this is all really easy to do. So that I'm aware of. So there's all the half integer return kernels. And then, of course, any they can all have a variance parameter and a length scale, as per usual. That's fine. Separately, you can have the sum of any two kernels. Gives any two kernels which have this Markov property. If you go for the GP that is the sum of them, then that will also have it. So sums of Markov GPs are fine. You can also do stuff with products of kernels that have the Markov property. Obviously, this doesn't really have an interpretation as a product of GPs because the product of two GPs isn't a GP, but the product of two kernels is another kernel. And if they both have the Markov, if each the GPs corresponding to each of the kernels have the Markov property, then the GP with the product of the kernels also has the Markov property. And then there are other things you can do that's slightly different. So there are things like, like the linear kernel has this Markov property, but it's kind of a bit of an edge case in that it's this degenerate kernel, and you only really need to know 2 points, and you have the whole function. You can also construct approximations for things like periodic kernels. But they actually wind up looking more like basis function approximations, where you you have like kind of a collection of pseudo points on the interval of your periodic kernel. And every time you see a new data point, you update all of them. Like you kind of propagate that whole state forward. So these tend, like the approximations here tend to wind up being quite high dimensional. So I guess the one thing I've not mentioned here, which I should definitely mention here, is really this scaling is order n times some constant d cubed, where d here is the dimensionality of the state vector for all of these things. So with the Matern 2 kernel, we saw that this whole state was just 2. It's just the process and its derivative. With Matern 5.2, there's 3 of them. Sums of these things, you have the sum of the total number of states in each of them. Products, I think it's the product of the number of states. So the point here, though, is that this value here, d, can blow up quite quickly for complicated kernels. But for kind of smallish sums of relatively simple kernels, this works really, really nicely. And particularly if you've got long time series, then this is, it's almost always going to be a better option than pseudo-point and kind of standard pseudo-point approximations. So sorry, rather long-winded answer.
Periodic kernel works? Because that's something that's not Markov. So how does this work for the periodic kernel? That's quite strange. It's Markov property.
Right. Yeah. So it's not that it has the Markov property; it's that we approximate it with a basis function expansion. So you can imagine if you've got a swap pane quickly. If you've got a periodic GP and the sample looks a bit like this, and this is the period, then you could construct like a basis function expansion of this and say that we're going to approximate this as like a sum over p terms of like some Gaussian coefficient, call it alpha p, and then some basis function p of like this interval, so just call it of x. And then if you make these like sines and cosines or something, then the total number of things you need here is capital P for whatever size your approximation is. And so then what you do is you take these and you each of these alphas here, so alpha p is like normal with some parameters. You make a state vector that is like all of the alphas, and propagate this forward 3 times. And the point here is like, because it's periodic, you don't need, you can kind of get away with this because it's periodic, and you only ever need like, you don't need an increasing number of basis functions as you see more and more of this periodic function, because it's just the same things repeating. And then the transition dynamics for this bit, so the conditional distribution of like alpha at t given, sorry, the conditional distribution of alpha at t given alpha at t minus 1 is just some deterministic transform. So it's like a degenerate normal or something like that. I think probably it's just I. Anyway, it's this kind of thing. So it's like, the point is, it's like a finite dimensional approximation to the periodic signal. So it's got like a slightly different feel to the other kernels. Does that make any sense?
Yeah, no, that's clear. That's clear how you do it with the basis functions. That's really clever.
Yeah. It's like, it's kind of annoying because the dimensionality becomes quite high if you've got relatively complicated stuff going on in your periods. But I guess it works quite quite well for relatively simple simple functions. Cool. So that's pseudo-points and Markovian GPs. Then there's one other bit of background that we need before diving into the papers, which is the structure of optimal Gaussian approximations to Gaussians with non-Gaussian likelihoods. So that was a bit of a mouthful. We went over this a couple of months ago when Matt and I did a presentation, but the general idea is if you've got a model whose joint distribution is of this form, so we've got a Gaussian prior with 0 mean, could be any mean, doesn't really matter, and precision lambda 0, and then a likelihood, and sorry, this is f here is n-dimensional, and a likelihood that factorizes across the dimensions. Then the optimal approximate posterior in the KLQ2 posterior sense, i.e. doing variational bays, is something of this form in the second line here. So it's got some mean vector, which is kind of less interesting than the precision. But the precision is the sum of the prior precision and a diagonal term. So this is saying specifically the optimal choice of Q has this form, which only has a total of 2n free parameters. So the thing that this motivates is restricting the family of Gaussians you consider as your posterior approximations to be ones of this form. It doesn't say how you find the member of the family that is optimal, but it does say, you know, it's in there. And one really helpful way to interpret this, which we'll lean on a bit later as well. So actually, I should say this has been known since 1999. This appeared in Titsias' thesis, and then there's this well-known paper from 2009, which my impression from reading the paper is that a number of people didn't pick up on this result, and they expanded on the result and told everyone about it. Yeah, so the interpretation of this is the optimal approximate posterior. Its density is proportional to like the prior density times a bunch of extra likelihoods, where Each of these is, say, a scalar thing with a one-dimensional lambda, and then some like pseudo data-y thing, which is a function of the exactly what's going on in this likelihood term, or both of these are. And so this is the same as saying the optimal approximate posterior can be expressed as the exact posterior under this like surrogate or approximate or pseudo model, whatever you want to call it. And so I guess the kind of the thing that was interesting about this originally was this like 2n number of parameters, or at least as I interpret it. Like if you knew nothing else about the structure in, say, the precision, it's nice to know that you only need 2n variational parameters to find the optimal Gaussian approximation. But the way that this is going to be useful in our context is slightly different. We're going to wind up utilizing structure in the prior precision and combining it with this structure here to get something interesting. I mean, it still has the reduced number of parameters property, but it's just we can do a bit more if we know something more about the precision. Yeah, you can do natural gradients in this kind of setup. It's all really nice. I'm not going to go into the details. Because it's kind of secondary importance. So the other thing to say here is that the same kind of, so this really is like an exponential family property. And the same thing holds for any exponential family with the same exponential family as the approximate posterior. But this also holds for pseudo-point approximations, this kind of interpretation. So Tang and Rich showed this a few years ago. It might have been known before that, I'm not sure. So yeah, the idea is if we've got the standard pseudo-point set up, so we've got our prior over our u's, our pseudo-points, and our f's, the place we're going to make observations, and then a likelihood which factorizes over all the f's. And the approximate posteriors of this form, the usual, as discussed before, some Gaussian over u, and then the prior, sorry, the prior conditional over f given u. Then, again, the optimal approximate posterior can be written as a, it has some mean, it has some precision, and the precision is the sum of the prior precision and a bunch of rank 1 terms, each of which is a function of the nth likelihood. So each of these things, is something like this. And one way you can interpret what we're going to see later is going to be there's going to be sparsity structure in these. Okay, so that's the kind of the background, and now we can get into exactly what they're doing in these papers. So this is back again to the figure we had at the start, and we're going to express this as like, okay, well, we've got this Markov property in the U's, and the conditional distribution over the nth latent state just depends on its immediate neighbors. So by Vn here, I mean like the U's associated with the Sn. So for S3, it's just U1 and U2. So again, we're going to assume that the likelihood factorizes. And then if you write down the elbow, you have the usual KL between the approximate posterior and the prior, but the reconstruction term is interesting. So it factorizes over n, and because of this conditional independent structure in the conditional distribution over Sn given all of the pseudo points, i.e. it just depends on the neighbors, the only pseudo points that we care about for the nth term in the reconstruction term are the neighbors of the observation we're interested in. And so, like, kind of before you do anything else, it's kind of this immediately gives you structure of the form to tell you what the approximate posterior tells you about Sn. You just need to know stuff about the neighboring pseudo points. You don't need to know anything at all about all of the other pseudo points, which immediately gives you something. But the really interesting property is that it tells you that the optimal approximate posterior precision matrix is block tridiagonal, which means that the optimal approximate posterior is Gauss-Markov, or Markov because it's obviously Gaussian because we said it's a Gaussian. So the way to see this is to first note that the prior precision is block tridiagonal. So this isn't something I should have discussed explicitly yet, but I should have. If you have a Gauss-Markov model, so if you have U, and you say that it's Gauss-Markov, so it's some product over maybe these also vary. This, then you know that this is block tridiagonal. So it's going to be something like 1, 1, 1, 2, 1, 2, 1, 1, 2, 2. You get this structure going on down here, and then it's 0 everywhere else. So you can draw this analogy between like, oh, and Markov property, block tridiagonal precision. And so to know that the optimal approximate posterior is Markov, you basically just have to know that the best choice for the approximate posterior precision is block tridiagonal. Now this expression is the thing that the optimal approximate posterior precision will satisfy. You can get this just from kind of either just like brute force rearranging stuff with Gaussians, or you can get it from like an exponential family manipulation route. Anything's fine there. And the key observation here is that, so we're taking the gradient of this this nth reconstruction term with respect to the entire covariance matrix. And the key insight is that it's just a function of two neighboring pseudo points. And so that means that this gradient, which is going to be a big old matrix, is going to be, other than like some block, 2 by 2 block here, which is going to have the gradient with respect to like the nth, the first element of this, so it's like grad C, sorry, there's going to have lots of indices here, like UM, grad C, UM plus 1. Sorry, this is not too easy to say, but anyway, the point is there's like a block here that is on the diagonal. Well, really, it's like a kind of a tridiagonal block. So these two are on the diagonal, and these two are kind of the neighboring bits. Everywhere else is 0. So when you add this, any one of these terms in the summation here to lambda u, the result is still block tridiagonal. So everything remains Markov. So then with that established, it's just a question like, how do you parameterize this? And the way they go about it in the first paper is to just parameterize the Cholesky of the precision, which is like, and they restrict that to be block tridiagonal and lower triangular because it's Cholesky. They show how to do natural gradients. There's some kind of tricky business associated with like exactly how do you work with this thing, because you need the like the inverse of a block tridiagonal matrix is not itself block tridiagonal, it's dense. But they just need the block diagonal of it. So anyway, they do some tricks, and it all kind of works out. And you can compute elbows and stuff like that. So the second paper, the interesting innovation from my perspective here is instead of explicitly parameterizing the Q of U, it goes about it through this like do exact inference in an approximate model perspective. So what they say, or what they do, is they parameterize the approximate posterior as just the prior times some terms where you've got this like pseudo data stuff and a modified Gaussian likelihood, which depends on both of the neighbors. Well, like it depends on two neighbors. So you've got this structure here. You've got the pseudo points in the background, and then they refer to them as sites. There's this idea of a site-based approximation. But so to work with this approximate posterior, you'd need to somehow be able to like normalize this because it's proportional, and so it's just doing exact inference in a model that looks a bit like a regular state space model. But the difference is that like in a regular state space model, this term the second term here would only depend on like but here it depends on a pair of points. And it turns out that you can extend standard filtering algorithms to work with this kind of thing, and so you can do filtering and smoothing and compute the log marginal likelihood of models like this, which lets you do all the things you need to do variational inference. And so to work with Q of U, there's only M things floating around. There's no N anywhere. So, and it's definitely linear in M because it's all filtering like algorithms. And then there's this DQ term. Of course, as we discussed before, like maybe M needs to increase with N. So maybe really there's this kind of dependence on N. But hopefully the total number of operations you need is some constant factor less.
Sorry, what's D again?
Sorry, D is the dimensionality of the state. So for a Matern 3-2 kernel, it's 2, Matern 5-2, it's 3. It's like this kind of small coefficient that depends on kind of some properties of the kernel you're working with. So
D cubed is not very important, basically.
I mean, it depends on the regime you're operating in. Like if you're operating in like the regimes where the state space approximation is good, then like you're in that regime because D is quite small. But if you had a really complicated kernel, or if you were doing some kind of spatiotemporal thing, then D can become quite big quite quickly, and you run into issues there.
Okay.
Yeah, I mean, I just like this figure, so I kept it in. So anyway, so you've got this model and the model that we had 2 slides ago, and you can do filtering and smoothing. So anyway, okay, so we've now established how they've gone about doing approximate inference, the family of approximations they consider, so on and so forth. As I said, they do a couple of other things. So if you're interested, they talk a bit about how you can do the same kinds of things with power expectation propagation, and some more traditional signal processing techniques, and some spatiotemporal stuff, but not going to go into that. So how do they find everything works in practice? Like if you do inference, if you use this to approximate inference, what happens? So we're just going to like I'm going to kind of dive into this table a little bit. So all the numbers reported here are negative log predictive densities. So this is like the the approximate posterior probability of marginal probability of the data. So it's things like Q of F star. No, sorry, Q of Y star, and some observation, averaged over lots of observations. So the sparse VI row here is standard variational pseudo-point approximations, so kind of standard Titsias 2009 or Hensman 2013 stuff. The S squared row is the doubly sparse variational GP, which is the name of the first paper that we went over. So this, I should say, this is a table from the second paper, so it's comparing against the doubly sparse stuff. The S squared CVI is what we've been talking about with variational Bayes. CVI here is conjugate computation variational inference. It's just the kind of the name associated with how you actually do natural gradients in the approximate posterior they propose. And then full CVI is the same as S squared CVI, but your pseudo points are the same as your inputs. So there's no, the approximation involved here is all to do with non-Gaussian likelihoods, as opposed to using pseudo points or not using pseudo points. So the first thing to note is the numbers for, so they use the same number of inducing input locations for all of the techniques, and the regular sparse VI stuff gets like slightly worse numbers than the doubly sparse stuff. And my interpretation of that is because the doubly sparse stuff, like each inducing input is associated with multiple inducing variables, inducing points, whatever you want to call them, because it's like the process and its derivative and maybe its second derivative and stuff like that. The number of like inducing points really is like slightly larger for this S squared stuff, which is how they get better, i.e. smaller numbers. And then similarly here, the S squared CVI stuff does slightly better than S squared VGP, which it doesn't look like it's significant under their whatever they're doing, but the reason for that might just be that they're generally, like, maybe it looks like on average they're finding better approximate posteriors using the second parameterization than the first. And the reason to think that this might be a thing is that the numerics associated with working directly with precisions tend to be quite bad. So for example, which is what we do in the S squared VGP stuff. So you'll notice, like, for some of the results all the way over here, they've not reported numbers. And this is when they've got a lot of pseudo points. And my understanding is that they couldn't get all the numerics to work out, and they were getting positive issues with the positive definiteness of their approximations and stuff like that. So the gist here is, okay, these like explicitly parameterized sparse precisions aren't amazingly numerically stable, but these things where you parameterize the approximate posterior and hence the precision as exact inference in an approximate model do tend to be really quite stable. So they're able to report results for all the data sets here for that parameterization. And like my experience with this has been that it's really stable. Like Kalman filtering generally, which is basically the class of algorithms we're using to work with these models, is really, really stable. Yeah, and so then going back to the first column, the final interesting number is this one at the bottom here. And so it looks like in this case, maybe just they don't quite have enough pseudo points to get the best numbers. But then if you look at some of the other examples, like in the second column here, like all of these numbers are all at like 0.924. And again, they're beating both the S squared and the sparse VI stuff. One of the really interesting things is, which I think is potentially where some of the limitations of this method, I guess not limitations, but one of the things to note about this kind of approach is, so for this electricity data set, I think these are all UCI data sets, they're getting much better numbers when they don't use pseudo-points, i.e. when they just do the state space approximation, which will take a bit longer, but doesn't have any pseudo-point approximations involved. They're getting much better numbers than they get with their approximation. And I think the interpretation of that is just, they just don't really have enough pseudo-points. And so the question would be like, for this data set, so they've got a ratio of about 1 to 5 points to pseudo-points at the minute. Now, how many pseudo-points do you actually need to approximate this well? Like maybe it's the case that they're gonna need 100k pseudo-points, in which case you're down to like a 1 to 2 and a bit ratio of points to pseudo-points. And so then you're kind of in the regime there of like, do we even want the pseudo-point approximation here? And I think this is like potentially an issue with time series problems generally, in that there tends to be quite a lot of high frequency information in a lot of problems, like certainly for things like audio signals and stuff like that. But certainly they found that for a number of problems, they've been able to find problems where that's not the case. Like you can get away with using quite a few fewer pseudo points than you have observations, which is great. So that's about all I wanted to say. So yeah, I really like this work. I think partly just because it's just kind of, there's lots of nice structure to exploit. I think also it is like, it's a very interesting class of approximations. There are a couple, I think there's a bunch of other stuff to do with it. Yeah. Any questions?
Cool, thanks, Will. I'll stop the recording so we can ask questions offline.
Right.
Great talk.